Hello, my name is Akshat Tangsale, and you're watching the recorded video for Introduction to Process Simulations in Chapter 4, and we are looking at equations of state. In this lecture, I'm going to talk about how we can select properties method, how to calculate specific volume for pure components and mixtures of gases using equation of state in Excel and in solver function and goal seek function in Excel, and also use Aspen Plus to perform thermodynamic calculations. Solving equation of states allow us to find the specific volume of gases. Now, simplest equation of state is the ideal gas equation of state, which you would have learned in high school as well as in the first year of engineering. However, when it comes to high pressures or low temperatures, the gases do not behave like ideal gas. The reason for that is there are certain assumptions built into ideal gas law, such as the volume of the molecules themselves being negligible, the force between two molecules or two atoms of gases, where it's an atomic gas, is negligible, and the ideal gas also assumes that the collision between the atoms or the molecules of gases is completely elastic, which of course we know it's not the case, because if you keep increasing the pressure of a gas, eventually it will condense. Likewise, if you keep decreasing the temperature of the gas, eventually it will condense, which means there is some intermolecular attractive force between the molecules which cause them to come together. Therefore, estimating this correct specific volume is really important so that we can size the equipment properly. If it's a pressure vessel, it becomes even more important that we use equation of states which can correct for the attractive forces between the molecules, it corrects for the molecule volumes, and it corrects for the inelastic collision between the molecules. So the first step to estimating a specific volume is to know the enthalpy and the vapor liquid properties of the mixture. Just looking at a quick history of the equation of states. So in early 1800s rather, we had the ideal gas equation of state, which was developed by Emily Capleron, and um, this tells you that the pressure is equal to the uh, uh, gas constant R multiplied by temperature divided by the specific volume. The specific volume is defined in terms of cubic meter per kilomole or liter per mole or similar units. So it's volume divided by the number of moles of that gas. So it doesn't depend upon the size of the system. However, cubic equations of state were later developed in mid 1800s to mid 20th century, and all of them have so far progressed on each of the assumptions that they built into ideal gas law. We, we will cover this in excuse me. We will cover this in greater detail when in 2162, when we look at the chapter 5, which is on single phase systems, which is also happening in this week. One of the earliest cubic equations of state was developed by van der Waals, for which he in fact won Nobel Prize. And in this case, as you can see here, it looks similar to ideal gas law, except here pressure is equal to RT over V minus B minus A over V squared. So this minus A over V squared is the attractive force, which in effect reduces the pressure that the gas exerts on the walls of the vessel. And V minus B in the denominator here tells you that there must be something happening which increases the pressure, which is the non-elastic collision. So later in 1940s, Redlich-Kwong equation of state came in, which introduced a minor variation in the equation developed by van der Waals, and then Swarov improved on Redlich-Kwong equation in 1972, and Peng-Robinson equation of state came in 1976. So all these equations of states are able to model certain systems better than the other systems. So it's important for us to know which ideal gas equation, which cubic equation of state must be used for modeling which system. For pure components, the parameters A and B are determined by their critical temperature and critical pressures and eccentric factor in some cases. Van der Waals equation does not have the eccentric factor, which was later discovered that obviously not all molecules are perfectly symmetrical. You can have short round type molecules, whereas you can have long floppy molecules. You can have branched molecules. So all of them will behave slightly differently, which wasn't known in the time of van der Waals. So that was introduced for the first time by Arke-Swove, or the equation that was modified by Swove based on the Regli-Kong equation. Peng-Robinson equation accounts for not just the eccentric factor but an extra factor. Uh, Sorry, that is in PSRK, Peng-Robinson, Strycek, and Weber equation, which introduce a kappa as well. So that's an improvement on Peng-Robinson equation, and is called as PRSV equation. So to model these, let's look at a work problem in using Excel goal-seek function. This is talking about N-butane at 393.3 Kelvin and 16.6 atmosphere. So as you can see, the pressure is high enough. Anything above 10 atmosphere, uh, ideal gas equation of state will not be able to model properly. So we need to look at other equations of state. In this case, it's asking us to use Arke-Swove equation of state, sometimes also called as SRK equation in some texts, but because the Aspen Plus calls it Arke-Swove, we are going to use the same terminology here. It asks us what is the specific volume predicted by ideal gas equation of state at the same condition. So we can compare the two ideal gas, the two specific volumes using ideal gas equation of state and using Arke-Swove equation of state. And later we will also look at Aspen Plus to estimate the specific volume and see if it predicts anything different. The data for N-butane is given from literature. The critical temperature is 425.16 Kelvin and critical pressure is 37.47 atmosphere, and omega, which is the eccentric factor, is 0.193. So to model, I've created a screen capture of Excel spreadsheet. So let's go through it. So initially set up the spreadsheet by entering all the data and given conditions, and then we can start setting up the variables. So the variables we're interested is in A, B, alpha, M, reduced temperature and pressure, and the V hat, which is specific volume. The equations are given on the right hand side. So if we start entering the details, A is equal to 0.42748 times r squared. So in this case, r is in the same units as we want our specific volume, which is liter per mole. So r will be liter atmosphere over mole Kelvin. You need to choose the right units for r depending upon the units of other variables that you have, like temperature and pressure. So once we have entered all the coefficients, all the parameters A, B, alpha, M, we will be setting up the formula for the Arke-Swove equation. So currently we are setting up the equation for B, which is 0.08664 times R times critical temperature over critical pressure. Alpha is in terms of another parameter M, and the reduced temperature. So it's 1 plus M times 1 minus reduced temperature to the power 0.5, and then the whole thing in the parentheses squared. At this stage, the values that we get are not going to be accurate until we solve the whole equation using goal-seek function. So let's set up the equation for M. M is equal to 0.48664 0.80 plus 1.574 times omega, omega being the acentric factor, minus 0.176 omega squared. This omega value may or may not be given directly, so for you, if you have to use Excel to model a problem, then you'll have to search for literature values. Sometimes you can use books like the Felder and Russo textbook, which we are using as a recommended text for CHE2162. Other times you can find it in the Paris Chemical Engineers Handbook. So now we have set up all the variables. We can start writing the equation of RK-SOF. We cannot use the equation in the form given here. We need to convert it into one-line equation and must be equal to 0 on the other end so that we can use the goal-seek function properly. So it needs to be written in the cubic form, v hat squared times p minus v hat squared times RT plus v hat times, in the bracket, 1 minus pb squared minus RTB, close brackets, minus AB equal to 0. So of course equal to 0 does not need to be written in the formula here. We are only going to write up only the left hand side of the equation. Okay, now that the equation has been set up, we can use the goal-seek function. As you can see, currently it shows the equation value to be equal to minus 1.1. It must be equal to 0. So we go to data and then what if analysis and click on goal-seek, and we need to equate this cell to 0 by changing the cell v hat. So it's going to estimate the v hat value. It gives us 0.168, but it's not quite equal to 0. So to make it go to 0, I'm going to multiply this number to a very large number like 1 million, and then try and make that cell equal to 0. So if this cell goes to 0, then naturally the previous cell will definitely be very close to 0. So as you can see, it gives us 3.97 10 to minus 12, and this one is 3.97 10 to minus 6. So that's pretty close to 0 on the formula cell that we wanted to be 0. That gives us a v hat value of 0.168768. Now we need to set up the ideal gas equation or state. So we do the same thing. We can use the formula for ideal gas equation or state, which is pressure minus RT over V hat equal to 0. In this case, I'm setting up as RT over V hat minus pressure, which should also be equal to 0. So again, we can use goal-seek function to make this go to the cell for the function go to 0 by changing the v hat cell. And this time we get a very different value. As you can see, the ideal gas equation or state estimates 1.944, but the actual value must be 0.168. So N-butane is compressed quite a lot, so the molecules occupy a much smaller molar volume than the ideal gas equation or state predicts. Let's look at the same solution in Aspen Plus. So in Aspen Plus, you open a new file, and either you can use a template or go with a blank sheet. I'm using a chemical unit with metric units, and then enter N-butane as the component, and we are going to use the method as RK-SOF in the method specification. Once you have selected this, we click on the analysis. So we click on pure system, look at the property molar volume of V, and select the component that we want, select the right units that we want, and enter the range that we want. So I'm here entering the lower limit as 393.3, which was the value that we wanted, and upper limit as 395. You can use the same value if you want, but I'm trying to get 5 data points here at the pressure that we want. In this case, it generates a graph, but we can also look at each data point by clicking on the results and have a look here. It gives you the at the given temperature of 393.3 and 16.6 atmosphere, it gives us a pressure of 0.137, whereas the uh, 137 in case of Aspen Plus, but in Excel we had got 0.16 rather, and in Aspen Plus we have received 0.137. So Aspen Plus predicts even smaller specific volume because it has other built-in thermodynamic properties which we are not able to capture directly in the Archimedes equation of state. You will notice that here the unit is cubic meter per kilomole, whereas we had earlier looked at liter per mole, but they are the same because it's multiplied and divided by 1,000. When it comes to estimating equation of states for mixtures, it becomes even more difficult because now we need to account for the critical temperatures and critical pressures of all the different gases. So often we have to come up with very complex equations, and the parameters A and B must be accounted for all the different gases. So since the parameters A and B come about from intermolecular potential energy, it can be justified that species 1 is in mixture of species 2. When the species 1 is in mixture with species 2, the molecule will interact very differently with the second molecule than with other molecule 1. So for example, if you have gases like nitrogen and hydrogen together and you compress them, nitrogen-nitrogen interaction will be quite different to nitrogen-hydrogen interaction. So that different interaction between two different types of molecule must be accounted for. So the interaction of molecule 1 with another molecule 1 will be same as the pure species, which we can assume, and that usually is the case. But the interaction of the interaction between those two molecules will be proportional to the mole fraction squared. So interaction of molecule 1 against interaction of molecule 2 will be proportional to the mole fraction squared. So here we get A equals to Y1, which is the mole fraction of molecule 1 squared times A1, plus 2 times Y1 times Y2 times the interaction between molecule A and B, molecule 1 and 2, plus y squared of 2, which is the mole fraction of molecule 2 times A2. And for mixtures, the parameter B is expected to have a linear equation in the form of B equals to Y1 times B1 plus Y2 times B2. So we can write the same equations as before for Wrigley-Kwong, Archimedes, Peng-Robinson, and others, but this time we have each component given here, but the parameters A, B, alpha will have a combination of all the parameters as we had seen before in the previous equation, and then in the actual equation of Archimedes we are going to use A and B computed from the sum of, or the weighted sum of all the components together. There's an additional parameter, this Kij for Peng-Robinson equation, called as the binary interaction parameter, and has been computed for many binary mixtures. It's given in the reference given below, but it becomes really hard for us to model these things using Excel. It can be done, but it's just a bit too hard. So for complex mixtures, when there are more than two, let's say, you can try and model up to two components in a binary mixture, but more than two components, it becomes really complex. So we're only going to use Aspen Plus for more than two components. So here I have a problem described as a mixture of gases in carbon monoxide, water, carbon dioxide, and hydrogen, Their molar flow rates are given. What we want to find out is the specific volume at 7 atmosphere and 500 Kelvin. The omega parameters have been estimated from the literature. So once again, in Aspen Plus, we are going to open a new file, and then add all the components. You can just enter sometimes the formula like CO, CO2. For water, you can enter water or H2O. And then we go to the property selection method and select RK-SWAV method and click on next. It will calculate all the binary interaction parameters, and then we can go to simulation environment. And then here we are going to create a dummy block like compressor, and then add two streams to it. In this case, the specific volume cannot be estimated directly using the property analysis method because this is not a pure system. So we enter the temperature and pressure details that we want for the feed stream to the compressor. So 500 Kelvin and 7 atmosphere. And here we enter all the molar flow rates. 630 kilomole per hour for carbon monoxide, 1130 for water, 189 for CO2, and 63 for hydrogen. And for the block, we can enter the details. We need to set up the specification. So we select an isotropic compressor, and the discharge pressure is slightly above the entering pressure, which was 7 atmosphere. So we can set up as 8 atmosphere. And that's not relevant because we're not going to look at the compressor product stream. We can go to the summary of the results and have a look at the stream table. So here you can see S1 was the feed stream, and unfortunately for us, the molar volume is not given. It's mass flow rate, mole flow rate, volume flow rate, and enthalpy. So we'll have to create our own customized stream table. So we click on streams customs, and then search whether this one has got the parameter that we want, the molar volume. It doesn't, so we need to add a new customized stream, and we can name it, let's say, custom. And once we have created a new custom stream, we can edit view and click on display options, or property selection rather, and we can search for molar volume. So in the text search feature here, enter molar volume and search for it, and click it to add to the mixture. And then you can scroll down and add all the parameters that you want to have a look. So I'm adding average molecular weight, mass density, and also the enthalpy flow. So once we have added the parameters that we want, have a look at the molar volume for the mixture. It gives us 5.809 cubic meter per kilomole. So this is how we estimate molar volumes so that we can size the equipment properly. You might ask how we can select a proper property methods. So this flowchart explains you the method, or you can use the Aspen method assistant also to guide you through the property selection method. First thing you need to look at is, in your components, is any one of the component a polar component? If not, then you can use the cubic equations of state that we have looked at, like SRK or RK-SWAV, Peng-Robinson, or Peng-Robinson's Tri-Chicken-Vera, PRSV. However, if you have any polar components like water, then we need to check whether the pressure is low or not. So if the pressure is above 10 bar, then we can use any advanced equation of state like PSRK or PC-Soft. However, if the pressure is lower than 10 bar, then we need to check whether there are any supercritical components. If there are no supercritical components, we can use any activity coefficient model like NRTL, which is non-random two-liquid model, or UniQuack, or other similar activity coefficient models. If you do have any supercritical components, which means any component which is above its supercritical temperature and supercritical pressure, Then we need to use an activity coefficient model with Henry's law, and the Henry's component will be the component which is supercritical. So that covers the selection for right property methods and how to estimate um, the molar volumes of components or mixtures using Excel and Aspen Plus. We are going to practice this in the uh, computer lab on Friday. So make sure you have done the work problems that I've done in this lecture, and then come prepared to solve the tutorial problems in the class, in the computer lab. Thank you, and have a good day. Bye.